ultimate sensor combination would be a 9-axis sensor paired with a GPS sensor. The 9-axis sensor would give you an object's orientation data, like acceleration, rotation, and heading. And the GPS sensor would give you the object's location data, like latitude, longitude, altitude, and velocity. With all of that data, you could detect pretty much every aspect of an object's position and orientation. In this video, we're going to learn how to set up GPS sensors and see how to work with the data they provide.
The GPS I'm going to use is Adafruit's Ultimate GPS Breakout. This is one of the more reliable GPS units you can get. The sensor chip is right here. The GPS sensor itself is the MTK3339 GPS from MediaTek. This tan area above the sensor is the ceramic patch antenna. There's also a UFL connection to connect an external antenna. On the back of the GPS, there's a coin cell battery holder. With a battery, the GPS will keep its satellite fixes after the main power is turned off. This is an LED that blinks to let you know if there's a satellite fix. Here's the 3.3 volt pin. This pin provides a 3.3 volt supply that you can use to power other devices. This is the EN or enable pin. It's high by default, but if pulled low, the GPS will turn off. This is the battery pin, VBAT. It's connected to the positive terminal of the coin cell battery. This is where you can input 3.3 volts from a coin cell battery on another device. This is the fix pin. It's connected to the fix LED. When the LED is on, the pin will be high. When the LED is off, the pin will be low. This is the TX pin. This is where data is transferred from the GPS to the Arduino. This is the RX pin. It's used to send commands from the Arduino to the GPS. This is the ground pin. It connects to the Arduino's ground pin. This is the VN pin, which connects to either 3.3 volts or 5 volts on the Arduino. This is the PPS pin. PPS stands for pulse per second. It outputs a signal to synchronize other microcontrollers to the GPS. We don't need to use it with the Arduino. Now let's see how GPS works so we can get a better understanding of how to use the sensor. GPS uses triangulation to detect your location on Earth. Global positioning satellites orbiting the Earth transmit a radio signal with information about its location and current time. The GPS sensor receives that signal and calculates how far away the satellite is, based on how long it took the signal to reach the sensor. That locates the sensor on a radius equal to the distance from the satellite to the sensor. With distance measurements to multiple satellites, the sensor can determine its exact location relative to the satellites. When the GPS sensor sees a satellite and receives a signal from it, it's called a fix. The GPS sensor needs a fix with at least 3 satellites to get a location reading. But more satellites will give you a more accurate location. The GPS uses TTL serial output to send data to the Arduino. This means we can view the raw sensor readings on the serial monitor without any libraries or code. To get the raw GPS readings, connect your GPS to the Arduino like this. The VN pin of the GPS connects to 5 volts on the Arduino. Ground connects to ground. The RX pin on the GPS connects to digital pin 0 on the Arduino. The TX pin connects to digital pin 1. Now we can just open the serial monitor and get the raw GPS readings. I'll upload this empty sketch to show you. It's done uploading, so now I'll open the serial monitor. Here's my GPS sensor connected to my Arduino. The GPS gets satellite fixes and starts sending data on its own. We're getting a bunch of numbers coming through. Let's take a closer look at this. These are called NMEA sentences. There are 4 different NMEA sentences in each sensor read. This GPRMC sentence is the one we'll be using the most. GPRMC stands for Global Positioning Recommended Minimum Coordinates. It contains most of the location information we're interested in. Each piece of information is separated by commas. The first piece of information is the current time in Greenwich Mean Time. This says 220739.000, so the GMT time is 22 hours, 7 minutes, 39 seconds, and 0 milliseconds. The second piece of information is a status code. This value is an A for active if the NMEA sentence is valid, and the GPS had a satellite fix when it got the data. If this is a V, it means the data in the NMEA sentence is void and should not be used. The third and fourth pieces of information are your latitude position. The GPRMC value for latitude are in this format. The first 2 digits are the degrees, and the second 2 digits are the minutes. The number after the decimal is the fractional component of the minutes reading. Then there is either an N or an S, depending on whether you're north or south of the equator. So my current latitude is 3244.8433, which is 32 degrees and 44.8433 decimal minutes north. The 5th and 6th NMEA values are the longitude. The GPRMC value for longitude is in the following format. The first 3 digits are the degrees, and the second 2 digits are the minutes. The number after the decimal is the fractional part of the minutes value. Then there's either an E or a W, depending on whether you're east or west of the prime meridian. So my current longitude is 11711.4519, or 117 degrees and 11.4519 decimal minutes west. The 7th NMEA value is the ground speed, in knots. My GPS isn't moving right now, and this is pretty close to 0 knots. The next GPRMC value is the course made good reading. This is the direction the GPS is traveling, independent of the direction it's pointing. It's the angle in degrees from true north. The 9th GPRMC value is the date of satellite fix. This tells you the current date in days, months, and years. I couldn't get the next 2 GPRMC values to output, but the next one should be the magnetic variation. And the one after that should be the direction of the magnetic variation, either east or west. The last piece of data in the GPRMC sentence is the checksum. It's used to verify that the sentence was transferred to the Arduino without errors. The next sentence is the GPVTG sentence. It contains the track made good and ground speed values. The sentence after that is the GPGGA sentence. It contains data about the fix quality and the number of satellites with a fix. And the last sentence is the GPGSA sentence. It contains more information about the fix quality. We don't have time to go over all the details about NMEA sentences, but if you want to know more, these two sites have a lot of good info. To get these NMEA sentences in a format we can work with, we need to parse them. Parsing means to simply read some text and convert it into something easier to read. To parse the NMEA sentences, we have to connect the GPS to the Arduino like this. Connect the GPS's TX pin to Arduino pin 3, and the RX pin to Arduino pin 2. The VN pin connects to 5 volts, and the ground pin connects to ground. We're going to use the Adafruit GPS library to program the sensor. You can download it from this link. The first thing we have to do is include the Adafruit GPS library. We do that with #include with adafruit_gps.h inside the brackets. Then we need to include the software serial library. The software serial library lets us create a new serial port to talk to the sensor. That way, we can use any digital pin to connect to the GPS's TX and RX pins. We include it with #include and software serial.h inside the brackets. Next, we create an object called mySerial from the software serial class. We pass the object 2 parameters. The first parameter is the Arduino pin you want to serve as the RX pin. In this case, we've connected the GPS's RX pin to pin 3, so I put 3 as the first parameter. The second parameter is the Arduino pin you want to be the TX pin. The GPS's TX pin is connected to digital pin 2, so I put a 2 in here. Then we create another object to use the functions in the Adafruit GPS library. I'm calling it GPS. We need to pass the mySerial object to the GPS object. Now we create a char variable called C. Each NMEA sentence is a string of characters. This variable will hold the individual characters in the string while we're reading it. Now in the setup, we initialize the serial monitor with serial begin. Then we initialize the GPS with the begin function from the Adafruit GPS library. That function is called through our GPS object. We pass the begin function the default baud rate of the GPS, which is 9600. Now we can tell the sensor which sentences we want to receive. Remember, the GPS returns 4 NMEA sentences in each read, but we don't need all of them. Most of the information we're interested in is contained in the GPRMC and GPGGA sentences. The Adafruit GPS library has a function called sendCommand. If we use this command as a parameter, the GPS will only send the GPRMC and GPGGA sentences. Set NMEA output RMC GGA. If you only need the GPRMC sentence, you can change this to RMC only. If you want all of the sentences, you can change this to all data. Now we set the update rate of the GPS. The update rate is how fast the GPS sends location data to the Arduino. We do that with the same sendCommand function, but now we pass it this command. Set NMEA update 1 Hz. The 1 Hz here sets it at 1 Hz. You can also use 5 Hz by switching this to 5 Hz. Or you can use 10 Hz by switching it to 10 Hz. Now, it takes a little time for the sensor to start up and perform these commands. So we should delay for a second to let the GPS initialize before we start reading NMEA sentences from it. Now we move down to the loop. The first thing we want to do is clear the serial buffer. I'm going to come back to this in a minute, so don't worry about this right now. NMEA sentences will be streaming out of the GPS at a rate of once per second. So we need to tell the Arduino to wait until there's a valid NMEA sentence to read. We do that with this while loop here. This makes the Arduino loop and wait until an NMEA sentence is ready to be read. The new NMEA receive function returns a true value when a new set of NMEA sentences have been received, and a false value when no NMEA sentences have been received. So with no NMEA sentence available to read, this not operator makes the condition true. So the program enters the while statement, where we use the library's read function to read the characters coming in through the serial bus. The characters are stored in the C variable. If there is an NMEA sentence ready, the new NMEA received function will return a true value. This not operator will make the condition false, so the program skips this section and continues on with the rest of the sketch. Once we get an NMEA sentence, we can parse it. The last NMEA function returns the last NMEA sentence received. We pass the last NMEA function to another function called parse. So this will take the last NMEA sentence received and parse it. Now we have everything we need to get the different pieces of GPS data. Let's start by printing out the time. First, we print out some text that says time equals. We're already familiar with printing to the serial monitor, so I won't explain how we're formatting the data here. The main thing is to see how to get the GPS data. Each piece of GPS data is stored in a public variable that we call through the GPS object. To get the hours, use the hour variable. For minutes, use minute. Seconds, use seconds. And for milliseconds, use milliseconds. You get the idea. Each variable needs to be accessed through the GPS object. To access the date information, use the day, month, and year variables. Notice the second parameter of these serial prints. The desc keyword makes the value print with a decimal point. You can also get information about the signal quality. The fix tells you if the GPS can see any satellites. It holds a 1 if the GPS has a fix, and a 0 if it doesn't. Fix quality tells you how strong the fix is. Satellites tells you how many satellites your GPS has a fix on. Now, we don't want to print any location data unless we know there's a fix. So we have an if statement with the fix variable as the condition. So this code will only be executed when there's a fix. Now we can print the location data. The latitude variable holds the numeric raw latitude value, the same way it appears in the NMEA sentence. The lat variable contains the cardinal direction, north or south. The longitude variable holds the numeric raw longitude value, also the same way it appears in the NMEA sentence. The lon variable contains the cardinal direction, east or west. To get the latitude and longitude in degrees, we can use the latitude degrees and longitude degrees variables. This 4 in the second parameter makes the numbers print with 4 digits after the decimal point. To get the speed data from the GPS, use the speed variable. The heading in degrees can be accessed with the angle variable, and the altitude can be accessed with the altitude variable. Then we print a line of dashes to separate each group of readings. Now we loop back up to the top of the loop section. Before we get the next set of NMEA sentences, we want to clear out the serial buffer to make sure there isn't any old data in it. This clear GPS function clears out the serial buffer for the next set of NMEA sentences. The function is defined down here. To clear the serial buffer, all we need to do is take a read, parse the sentence, and then do nothing with it. We read the GPS the same way we did it earlier, with a while loop that makes the Arduino wait until a sentence is ready to receive. When that happens, the sentence gets parsed, but we don't do anything with it. We do this twice, once for each NMEA sentence. Once that's done, we return to the loop section where we wait to receive a sentence we're going to keep. That's all the coding we need to do, so let's check this out. Here's my GPS connected to the Arduino. You can see the LED blinking here. It blinks once per second when there's no satellite fix, and once every 15 seconds when there is a fix. You usually need a clear view of the sky to get a fix, and depending on where you are, it can take a minute or two to get a fix. There we go, looks like we got a fix now. And we're getting some data coming through. Let's pause this for a second. The first bit of data is the time, in Greenwich Mean Time. We have the hours, minutes, seconds, and milliseconds. Then we have the date. The format is the day, month, then year. Here's our fix and fix quality. This is how many satellites we have a fix on. And here's the location coordinates. This is in the same format as it is in the NMEA sentences. Then we have our coordinates in degrees. You can put these coordinates into Google Maps, and it will show your location. Next we have the speed, which is in knots. We also have our heading and our altitude. And that's about it. We've gotten a lot of data out of the sensor. You can probably see how useful it would be on a remote control vehicle. And paired with a 9-axis sensor, you'd have all the data you need for complete control over it.
The 3-in-1 Smart Car and IoT Learning Kit from SunFounder is a hands-on, all-included electronics kit that is perfect for anyone who wants to learn how to master the Arduino. The kit comes with an Arduino, 22 different sensors and modules, breadboards, jumper wires, and everything else you need to build a bunch of fun and interesting projects. Learn about robotics by building a remote-controlled smart car that can be controlled with an infrared remote controller, or drive on its own and avoid obstacles or follow a line. Learn about the Internet of Things with a project that lets you monitor the temperature, humidity, and light level of a room from an app on your smartphone. And build a plant monitor that tracks the temperature, humidity, light intensity, and soil moisture, and displays it on your smartphone so you can keep your plants watered remotely. It's a super cool kit, and I had lots of fun building all the projects in it. So click the link in the description below to order the kit from SunFounder.